This is lesson 2.3 on identifying the domain. So recently we introduced a couple of different ideas. We talked about relations. We said that a relation is just a collection of ordered pairs. We also talked about a special type of relation called a function. A function is a relation where we don't have any repeats of the first coordinate, or we'd like to think of it as the x-coordinate. When we have a function, we can actually talk about this for a relation in general, actually. The domain of a relation, or the domain of a function, it's going to be the collection of all of those first coordinates. So when we have a function, we can think of the domain as the collection of all of the inputs in some sense that give us an output. So basically, it's all of the x values that give us a valid y value back. Now, if we have the graph of the function or the graph of the relation, it's actually pretty easy to identify what the domain is. It's also easy to identify what the range is. The range is going to be the collection of all of the second coordinates, the collection of all the y values. If all we have is the rule itself, though, like x squared minus 1 or square root of 5x plus 2, finding the range is a little bit trickier. Finding the domain is a little bit trickier, but it's not too difficult to do. We're going to focus on that last bit. When we're given the rule of a function, how can we find its domain? Basically, we're going to avoid the bad things. We want to avoid dividing by 0 and taking the square root of a negative number. And if we can find all the values of x where we avoid those bad things, that's going to be our domain. So here's one example. Find the domain of the function 3x plus 7 over square root of 4x minus 6. As I mentioned before, the two main things that we want to avoid are dividing by 0 and taking the square root of a negative number. Those are not the only things in mathematics that you need to avoid, but for our purposes, the functions that we're going to run into, those are really the only two things that you need to be on the lookout for. When you introduce trigonometric functions, talking about tangent, cosecant, that sort of stuff, then you've got to introduce a few other things. Logarithms, you got to introduce a few other things. So, but for right now, we're just going to worry about these two things: square roots, or really even roots, of negative numbers, and dividing by 0. So in this case, the numerator, we could care less what the numerator does. It can go off to Europe for a week. Who cares? It's the denominator that we really need to pay attention to. So since this is in a square root, we want to make sure that it is positive, or at the very least that it's not negative. There is a difference. And we don't want it to be 0 because it's in the denominator. So what we need to do is we need to figure out where is 4x minus 6 bigger than 0. Now, if this square root were in the numerator, it would be okay if it equals 0, but since it's in the denominator, we can't divide by 0. Hence, we have strict inequality. So this is a nice linear inequality. We can solve this pretty easily. 4x is bigger than 6. Divide by 4. That gives us 6/4, which we know is just 3/2. So in interval notation, I always want us to write our final answer in interval notation. Our lowest bound is 3/2. We don't want x to equal it, so we'll use an open bracket. And then we're not specified an upper bound, so we go all the way to infinity. So the domain of the function here is 3/2 to infinity. So here's another one. Find the domain of the given function. F of x equals square root of 6 minus 3x over 2x plus 4. Now don't let this f of x throw you off. Technically, I should have included it with the last example as well. This notation is just here to tell us we are defining a function as defining f here rather as a function of x. So I should have included it with the last example, and I didn't. Within the context, it was clear what we meant, but technically we should go ahead and name our function like we have here. Okay, so just like before, the two things we want to avoid: we don't want to take the square root of a negative number, and we don't want to divide by 0. So notice this time our square root is in the numerator. So all we need to do is to be positive, or at the very least, again, not negative. If it equals 0, it's okay. So the two things we want to take into consideration: the first one, we want 6 minus 3x to be bigger than or equal to 0. Equaling 0 is okay this time because we are in the numerator. And the other thing we want to take into consideration is the denominator. We want 2x plus 4 to not equal 0. We don't want to divide by 0. So we're going to solve these two guys. That's going to give us our final answer. We're going to put them together. We want both of them to be satisfied. So we have 6 is greater than or equal to 3x. Divide by 3. That tells me that x needs to be less than 2. So x is less than or equal to 2. So let me go ahead and just flip that around. I don't know about you, but I'm used to seeing the x on the left-hand side. So notice when I just flipped it around, I took the direction of the sign with it. It should stay pointing towards x. Over here, I want 2x to not equal negative 4. So dividing by 2, I want x to not equal negative 2. So if we try to put these together, try to think about what this would look like. If you can't look at it and see it, and I usually can't, go ahead and do what we did before when we had complex inequalities. Draw a number line. So x is less than or equal to 2. So here's 2. We'll put in a solid dot because it's okay if it equals 2. We're going to shade to the left, but not too far. Let's go ahead and put in our negative 2. We don't want x to equal negative 2, so we'll go up to 2, skip over it, but anything less than negative 2, it satisfies this, so we will continue on. So we want to take any number in this shaded region. So our leftmost bound of this first region, notice we basically have two regions to worry about. There's no left bound for the left region, so we're going to put negative infinity. We go all the way up to negative 2, but we don't want to equal 2, so we'll put an open bracket here. Then we pick right back up at negative 2. Again, we don't include negative 2 itself, but we include its immediate neighbors. In the second region, we go all the way up to positive 2. In fact, we include it. We have a solid dot, so we'll use a closed bracket here. And that's our final answer in interval notation. So once you get to this point, don't forget to go through this process of putting things into interval notation. It takes a little bit more time, but that is considered to be part of the problem. So again, when in doubt, go ahead and draw a quick little number line just to see what's going on. That'll usually help straighten you out, help you see what's going on.